Why rockets fail or space launches fail. Hi, welcome to Meng Updates. Today we will see the reason at the back of most space launches and rockets' failure. What do you think the most reason for the space mission failure? Identifying the single most cause for a rocket failure is difficult because launch failures are often the result of a combination of factors. However, one particularly challenging cause to address is anomalies related to propulsion systems, especially those involving rocket engines. Rocket propulsion systems are complex, high-performance systems that must operate reliably under extreme conditions of temperature, pressure, and vibration. Anomalies in propulsion systems can have catastrophic consequences for rocket launches, including partial or total mission failure. Here are several reasons why addressing propulsion system anomalies can be especially challenging. 1. Complexity of rocket engines. Rocket engines are highly complex machines with intricate designs and numerous components. Even small defects or malfunctions in critical components, such as turbopumps, valves, or combustion chambers, can lead to engine failure. 2. Extreme environment. Rocket engines operate in harsh environments characterized by high temperatures, pressures, and dynamic forces. The intense heat generated during combustion and the rapid expansion of exhaust gases place significant demands on engine materials and cooling systems. 3. Testing limitations. Fully testing rocket engines under simulated flight conditions is challenging and costly. While ground testing can uncover many potential issues, it's impossible to replicate all aspects of a rocket launch environment accurately. 4. Limited failure data. Rocket failures are relatively rare events, and data on propulsion system failures may be limited. This makes it challenging to identify patterns or common failure modes and develop effective mitigation strategies. 5. Integration complexity. Rocket engines must integrate seamlessly with other vehicle systems, including avionics, guidance systems, and structural components. Anomalies in propulsion systems can have cascading effects on other subsystems, further complicating troubleshooting and analysis. 6. Propellant challenges. The handling and management of rocket propellants introduce additional complexities and risks. Cryogenic propellants, in particular, require careful handling and storage to prevent leaks, boil-off, or other hazardous conditions. Addressing propulsion system anomalies requires a multidisciplinary approach, involving expertise in aerospace engineering, materials science, fluid dynamics, and propulsion technology. It often entails comprehensive testing, advanced diagnostic techniques, and collaboration between industry, academia, and government agencies. Despite the challenges, ongoing advancements in propulsion technology, materials, manufacturing processes, and reliability engineering continue to improve the performance and safety of rocket engines. By systematically addressing known failure modes, conducting thorough post-failure investigations, and implementing lessons learned from past failures, efforts are made to minimize the risk of propulsion-related anomalies and enhance the reliability of rocket launches. According to a paper published in Springer by Arif Göktürk Karakalioglu and Angie Buckley by studying launch activities between January 2000 to July 2014. Within this period, a total of around 1,000 launch activities have been recorded, more than 90% of which were satellite injections into Earth orbit. They found that the first cause is propulsion system malfunction, and the second cause as flight control system malfunction. 1 Propulsion system malfunctions. 9 of the propulsion system failures are associated with design glitches. However, in all of these 9 instances, the failed propulsion system had been used for the first time in flight. For all of these design-related problems, the propulsion system was redesigned and in no case the problem repeated. These redesigned systems performed flawlessly during their subsequent launches. The rest of the propulsion problems, 25 out of 34, were manufacturing and integration related. 2 Flight control system malfunctions. Majority of the flight control system malfunctions are based on erroneous coding of the flight program. In other words, human-induced software problems. In few other cases, the onboard computer suffers from hardware problems. Three-stage separation system malfunctions. The causes of separation problems mostly remain unrecognized. This is likely due to the complex character of these systems. A separation system can suffer from problems, which can have structural, electrical, electronic, pneumatic, hydraulic, or pyrotechnic origin. For guidance and navigation system malfunctions, the guidance and navigation subsystem appears to be one of the most reliable systems of the launch vehicles examined in this study. Only 2 launches had been failed due to GNS problems, and the root cause of one of these failures was human error. The root cause of the second malfunction could not be defined. 5. Structural disintegration. The failures related to structural problems constitute a minor portion of the launch failures. During one of the failures, the Pegasus XL rocket was deployed from an altitude lower than its operation range, which led to its structural failure. In the second event, launch of GSLV suffered from a faulty design/manufacturing of its shroud. It should be noted, identifying a failed subsystem may allow the failure investigation teams to determine the proximate cause of the malfunction, but not the root causes. In most of the examined cases, subsystem failures were outcomes of other problems in the system, which may not necessarily be related with that particular subsystem. Thermal system failures can significantly contribute to rocket and space launch failures, as the extreme conditions of space and the complexities of launch operations place significant demands on thermal management systems. Here are several ways in which thermal system failures can influence launch missions. 1. Engine overheating. Rocket engines generate intense heat during operation, and inadequate thermal management can lead to overheating, degradation of engine components, or even catastrophic failure. Insufficient cooling or thermal protection systems can compromise engine performance and reliability. 2. Propellant handling issues. Cryogenic propellants, such as liquid oxygen and hydrogen, require precise thermal control to maintain their temperature and prevent boil-off or excessive thermal stresses. Failure to properly manage propellant temperatures during loading, storage, or flight can result in loss of propellant efficiency or structural damage to tanks and plumbing. 3. Avionics and electronics cooling. Electronic components and avionics systems on board rockets and spacecraft are susceptible to overheating due to high ambient temperatures, internal heat dissipation, or inadequate cooling mechanisms. Thermal system failures in avionics can lead to sensor malfunctions, communication disruptions, or loss of control. 4. Payload thermal management. Satellites and scientific payloads often have stringent thermal requirements to ensure proper operation and instrument performance in space. Inadequate thermal protection or control systems can lead to thermal stresses, temperature fluctuations, or damage to sensitive payload components, compromising mission objectives. 5. Structural thermal stress. Thermal expansion and contraction of structural components during launch and orbit insertion can induce mechanical stresses and deformations that exceed design limits. Thermal gradients between sunlit and shaded areas of the spacecraft can cause differential expansion, leading to structural fatigue or alignment issues. 6. Thermal protection during reentry. Spacecraft re-entering the Earth's atmosphere experience extreme heating due to aerodynamic friction. Thermal protection systems, TPS, must effectively dissipate heat to prevent overheating and structural failure. Failure of TPS materials or design can result in loss of vehicle integrity or mission failure during re-entry. 7. Spacecraft thermal control systems. Spacecraft rely on active and passive thermal control systems to regulate internal temperatures and protect onboard systems from temperature extremes. Failures in thermal control subsystems, such as coolant leaks, pump malfunctions, or radiator blockages, can disrupt thermal equilibrium and jeopardize mission success. 8. Spacecraft thermal vacuum testing. thermal vacuum testing is essential for simulating the harsh conditions of space and verifying the performance of spacecraft thermal systems. Inadequate testing or unforeseen thermal anomalies during testing can lead to thermal system failures during actual space missions. Addressing thermal system failures in rocket and space launches requires robust design practices, thorough testing procedures, and continuous monitoring throughout the life cycle of the vehicle. By implementing effective thermal management strategies and ensuring the reliability of thermal control systems, space agencies and aerospace companies can minimize the risk of thermal-related failures and enhance the success rate of space missions. Addressing thermal management problems is therefore a critical aspect of rocket and space launch engineering, and failure to do so adequately can indeed increase the risk of launch failures or mission complications. Recent research in thermal management for rocket and space launches has focused on several key areas aimed at improving efficiency, reliability, and safety. Some of these research directions include: 1. Advanced thermal protection systems, developing innovative thermal protection materials and systems to withstand the extreme temperatures experienced during atmospheric re-entry. Research focuses on lightweight, high-temperature materials with improved thermal resistance and durability, such as carbon composites, ceramic matrix composites, and ablative materials. 2. Active thermal control systems, advancing active thermal control systems, such as pumped fluid loops, heat pipes, and phase-change materials, to regulate temperature and dissipate heat more effectively in spacecraft and launch vehicles. Research aims to optimize system performance, energy efficiency, and reliability while minimizing mass and volume constraints. 3. Thermal modeling and simulation, enhancing computational thermal modeling and simulation tools to predict and analyze thermal behavior in complex launch vehicle and spacecraft systems. Research focuses on developing accurate numerical models, incorporating multiphysics phenomena, and leveraging high-performance computing to simulate transient thermal effects and optimize thermal management strategies. 4. Adaptive thermal control, investigating adaptive thermal control techniques that dynamically adjust spacecraft surface properties or thermal insulation to optimize heat transfer and maintain thermal stability in varying environmental conditions. Research includes the development of smart materials, coatings, and surface treatments with tunable thermal properties. 5. Thermal energy storage systems, exploring thermal energy storage systems for spacecraft and launch vehicles to mitigate temperature fluctuations, manage thermal loads, and provide backup power during eclipses or extended mission phases. Research focuses on phase-change materials, regenerative heat exchangers, and thermal storage subsystem integration. 6. Thermal management for electric propulsion, addressing thermal management challenges associated with electric propulsion systems, including ion thrusters, Hall effect thrusters, and plasma propulsion. Research aims to optimize thermal control strategies, mitigate thermal gradients, and extend the operational lifespan of electric propulsion systems. 7. Thermal control for small satellites, developing lightweight and compact thermal control solutions tailored for small satellites, CubeSats, nanosats, with limited space and power budgets. Research includes passive and active thermal management techniques, miniature thermal control devices, and thermal modeling tools optimized for small satellite applications. 8. Thermal protection for lunar and planetary exploration, advancing thermal protection technologies for spacecraft and landers destined for lunar and planetary exploration missions. Research focuses on developing thermal insulation, coatings, and radiator systems optimized for extreme temperature variations, vacuum conditions, and radiation exposure in space environments. These research efforts are driven by the growing demand for innovative thermal management solutions to address the evolving needs of space missions, including long-duration human spaceflight, planetary exploration, satellite deployment, and space tourism. By advancing fundamental understanding, exploring new materials and technologies, and integrating multidisciplinary approaches, researchers aim to enhance the reliability, efficiency, and sustainability of thermal systems for rocket and space launches. Thank you. Please consider subscribing my channel. Till the next video, have a nice time. Bye.